All right, can you guys hear me okay? All right, welcome to Script All the Things, Reverse All the Malware, an introduction to Jython-Enhanced reverse engineering with Ghidra. So before I get started, I just want to introduce myself a little bit, so you guys know what I do. I come from a computer science background, software development as well. I'm an associate on the Coal-Fired Systems, the Federal Labs team. So that means on a day-to-day basis, I can be doing any number of things, ranging from network or application pen testing to malware analysis and looking at breaches. All right, so what are we going to cover today? My goal during this presentation is to take a look at a new tool that was released by the National Security Agency back in March of last year, and kind of highlight some of the features that you don't see that often in online tutorials on how it works that I think are a really powerful part of the reverse engineering process, especially for malware analysts. So I'm going to start by kind of talking a little bit about what the problem is when we do static malware analysis and what makes it so difficult. I think that's important to understanding why these tools are so powerful. And then I'm going to take a little bit of time to talk about Ghidra and some of its core features and some of the things that really set it apart from other solutions. And the big part of this, we are going to do a case study of a real piece of malware that's been found in the wild. Take a look at some of the things it does and ways it hides from analysts. And then we're going to use Ghidra's features to take those apart, undo them, and learn a lot about what it's actually trying to do. And then last part, takeaways, and I'm going to talk a little bit about next steps, things that I'm working on that we'll maybe see next year. And then open up time for questions once we're done. So we're going to start with our first question. Why is static analysis so hard? By this, we're talking about we have a piece of malware from an incident response or something like that if you're on a blue team, and we want to take it apart. One of the things we're going to do is we're going to look at it at a binary level. And the problem with it is that from an analysis standpoint, we have a pretty big lack of context. This is the key to why these things are so hard to take apart. Part of this is kind of inherent to any compiled code. Once we go from source code to a binary, it's designed to be easy for a computer to interpret, not for humans. We lose a lot of the context that you have in source code, things like variable names and function names and parameters and all this stuff that kind of gets stripped out most of the time. So the job of a reverse engineer, especially in the malware world, is to be able to go back and kind of try to figure out some of that context. Because that's how we tell what is this thing trying to do, what kind of things is it trying to get to, and so that's really what we're trying to find. Now, once you introduce a piece of malware that's actively working against you and it starts adding things like obfuscation, encrypting itself, encoding, packing, things really get crazy. And there's a picture I think I found, it's actually an emoji, that I think represents a pretty accurate representation of an analyst when he's working on particularly hard malware. There's a lot of been times when that's what I've looked like. All right, so on the other hand, luckily, technology gives us its benefits is that we've been able to develop a lot of tools to make this process easier. Now, in most cases, this involves static analysis tools. Commonly heard one is called IDA. Some of you, how many of you have actually had a chance to use it? Oh, okay, awesome. So that's been the big one. For people who are getting learning, it's a little bit, there's a free version as well, and then there's also a decompiler as another feature of that as an add-on. But we got, us reverse engineers got a little bit of an early Christmas present last year. In March, the NSA open sourced Ghidra, which is a open source, completely free, full-featured reverse engineering platform for software. And to sum it up, it's pretty awesome. First of all, it's written in Java and C++. This decompiler is the one part that's really written in C++. The most of the rest, the user interface, is written in Java. At its core, it's a disassembler and a decompiler. It supports 15 different architectures. That's not if you include variants like 32 versus 64-bit. 15 different types of architectures. And we're going to talk a little bit why that's so easy in Ghidra in a few slides. And on top of that, it's also got a pretty robust set of analysis capabilities. We can do things like detect functions in binary code. We can do control and data flow analysis. We can tell what functions are accessing what variables, what functions are calling other functions, things like that, which are really useful during the reverse engineering process, and they're pretty critical to what we do. It also does metadata analysis. As part of the analysis process, it does all the things like parsing PE binary headers to figure out a lot of different data that we can use to determine whether something's malicious or not. And it also has, and I have to admit I haven't experimented too much with this, but it also has the ability to do function fingerprinting. It can take known signatures of known code blocks, for example, binaries from a certain library, and it can take a executable you put into it, and it can identify, okay, this is something from, I don't know, Boost, which is a library commonly used. It has a bunch of different tools to supplement standard libraries on Windows or Linux. And that's kind of like, I guess, IDA's Flare. It's a kind of a counterpart to that. And this is one of the really cool things. It also has a pretty in-depth data type and function database. It has pretty much all the different Windows API functions that you might use if you're doing low-level Windows programming. It's got them in there. It has their names, what kind of types they pass, a bunch of like structures that you would use if you're a C programmer. And it can annotate the decompiler output with a lot of this cool stuff. So as far as features that really set it apart, I think the first one I'm going to talk about is how it does analysis of code. A lot of pieces of software that do this all kind of as one big monolithic process. But Ghidra takes a slightly different approach. It's completely modular. When you start with a binary, it's first you start with machine code, which is x86 machine code that it will interpret. And it instead parses this into what's called P code. This is a architecture agnostic language, kind of akin to what a compiler would use for those of you who work with compiler internals. It's really a register transfer language. And basically, this allows us to totally separate the CPU architecture from what's happening within the actual CPU state. This is part of the reason why we have 15 different architectures, because we can just add a new architecture by basically creating a configuration file that defines how each CPU instruction changes the CPU state. And then once we got this P code, we can then go from there and do analysis that allows us to generate pseudocode, not actual, like a level above assembler, which is makes the whole analysis process trying to figure out what's going on a lot easier. And on top of all this, we have a Java API, which is perhaps the coolest part. Now, I know IDA, for example, has their Python libraries or C++. Cool part about this is it's on one level above what you see in other pieces of software. We have the ability in the Ghidra API to work at the level of, okay, I want to look at a certain function, and that data, once we've gone through this analysis process, can be exposed, and we can take a look at what's going on, do some kind of whatever kind of analysis you want, and then annotate your disassembly or decompiler output to show you what you found, or edit it, or add comments, stuff like that. So it's super powerful. Just to give you an idea of what it looks like. This is an example of a couple functions I pulled out of the Ghidra API. This is at the Java level. There's also a Python interpreter, which I'll talk to you a little bit more in a little bit. Just for example here, let me see if I can pull this. I'll do it without a pointer. This is kind of the kind of things you'd be interacting with. For example, it has an object, a class, a Java class for a function. This is a piece of something that you would call, for example, use an example, a Windows library function, load library, for example. That would be something that you might be able to find in something like this. You can, for example, look at the parameters it takes. You can look at what functions call it, what functions it calls. We can even interact with the output of the analysis and put a comment there to say, okay, something else is going on here. We kind of do that whatever we want. And for example, in a CPU instruction at a lower level, we can get its address, where is it in memory. We can figure out what instruction is next. For example, if you have a bunch of data that's in between two instructions, it'll automatically skip all that and go right to the next one. And like, for example, if an instruction takes data as input, we can see there's a get input objects. For example, how many of you guys work with x86 on a regular basis assembly? Look at it. Okay, good number of them. There's an instruction called the push instruction, which is used to put data onto the stack. And generally what you do is you have push and then the name of a CPU register. And using this getInput objects, we can figure out what register that is, and in some cases even figure out what its value is. And then there's also a getResults object, which basically tells you what that instruction changes. Now, to interact with this API, you can basically write scripts, either in Java or in Python using Jython, which basically integrates with Java bytecode. Any Java library, it can call it as if it's built in. You can see here from the screenshot, I don't know if you can see, there's out of the box, there's more than 200 different scripts that the NSA included in here. These vary from actually useful tools to just kind of examples to get you started on your own project. And normally what you do, you can edit it directly in a piece of software, or you can do it in Eclipse. It has integration with Eclipse. So you can actually connect the two and be editing your script in Eclipse and have it go back and forth to Ghidra, which is super useful. Or you can just write it in your own text editor if you want to. Now, to run one of these, you can also see that there's a column there that's mostly empty. You can actually take Ghidra scripts and bind them right in there. You can bind them to a keyboard shortcut. So if you have something that you're using a bunch, you can put in the keyboard shortcut you want to use, and from then on, you can launch that script just by putting in that keyboard shortcut. So it's pretty powerful. And it also has, I might add, if you're doing this and you don't want to actually write the script out, there's also a full-on Python interpreter as well that you can use to interact with the analysis and results. It has pretty much access to, if you can do it in the user interface, you can do it in a script, which is pretty awesome. All right, so now that we talked a little bit about Ghidra and its features, I'm getting into talking about SpyEye. This is going to be the subject of our case study, really. For those of you who don't know what it is a piece of banking malware that originated in Russia, and I think it was around 2009 is when it was first discovered. It has a lot of cool features if you're a cyber criminal. I could do things like steal people's passwords. It had a keylogger in it. It could steal inputs from web browsers. It would actually interact directly with Internet Explorer and inject code into your web pages so that it could steal your banking information right off of it. It's detected and should be detected in pretty much any endpoint solution nowadays, since it's pretty well known and well studied. But it's actually, if you want to get into malware analysis and reverse engineering, it's actually a great place to start, because it has a lot of these cool reverse engineering or anti-reverse engineering techniques, kind of obfuscations that are pretty common in the malware world, but not enough to the point where it's really a pain in the butt to take it apart. I like to say it's interesting, but not too interesting. So now I got this binary. I'm going to start into this reverse analysis process. The first thing I'm going to look at is look at how it interacts with the Windows system. This is kind of the key. If we can figure out how a binary interacts with Windows, we've solved half of the problem, because we don't have to reverse any of the Windows stuff. We know what it's going to do because there's documentation. So at that point, we're going to look at the first thing we're going to do is look at the binary. It's got some interesting data in there in a second that Ghidra parses out. And one of the things is import tables. For those of you who deal with Windows internals, this is a list of libraries and functions that a binary needs to use. Because Windows is changing its libraries all the time and changing the functions and how they're implemented, where they're going to be in memory changes a lot. So it could be one time you run it. If you run it 2 months later, it could be a totally different place. So that gets into the whole thing of dynamic library loading. And the way Windows deals with this is it uses function import tables. Ghidra pulls these out and will tell you what Windows functions a binary will use. I've got this as an example. I've got a legitimate executable. This is actually Process Explorer. It's an internals tool. And I can see if I can pull this up here a second. I can pull up my mouse so I can point it. Can you guys see that? OK. So we can see that there's a bunch of different functions: close handle, create thread, create process, a bunch of different stuff that it wants to use. This is really powerful for us as an analyst. We can tell a little bit about what Process Explorer is trying to do. Now, Process Explorer is, I guess, a fairly good example because it tries to do a lot of stuff. It's pretty tightly, it does a lot of interaction with Windows. So we can see there's a lot of different functions. This is just one out of 4 or 5 different libraries that it tries to use. And Ghidra does a lot of cool stuff with this information. If we pull up the decompiler, which is one level above the disassembly, the pseudocode, we can see that it actually annotates. Anytime we try to use, for example, in this leave critical section, that's in the import table, it can identify that, okay, this is called a leave critical section, and it renames it in the decompiler, which is super useful. This is pretty close to what you'd see in any C program. And I don't know if you can also see it, but it also is able to interpret data types. So for example, leave critical section, I'll go over the mouse. You can see that the first thing in the Windows documentation, the first argument that it takes is of type LP critical section. This is a Windows API structure. And Ghidra has basically said, oh yeah, that variable then must be this. You can kind of see it's a little bit lost over here on the side. You can see that variable is an LP critical section structure, and it's able to put that in as an extra information. Now, it's a little bit different if we look at SpyEye. This is what we get. Keep in mind, I said earlier, it does a lot of stuff. It can interact with Internet Explorer. It is able to do key logging. It's a lot of things that it does interactions with Windows. But if we look at the list of functions that it imports, pretty short. Something's going on here. So just to give you an example of what that this kind of does, both in the decompiler and to the person reverse engineering it, it's not quite as useful. We can see here that all these functions that we have are just hexadecimal values. They're used by Ghidra to tell which function's which. They're basically, you have the FUN tells you that it's a function, and the other digits are where it is in memory. So we got to figure out what's going on here. All right, so next step is to talk. I want to take a little quick detour to go a little bit more detail about how import tables work, because it's useful. I got into here is just an example, kind of what we're dealing with here. I kind of like to think of it like a menu at a restaurant. We've got a list here. This piece of software has a list, hypothetically, of software, of libraries and functions it wants to use. It doesn't know where they are before it starts. So Windows, when it's launching an application, will take a look at all these. It will load each of those libraries. In this case, it would load win32.dll, and it'll load wininet.dll into memory. And then it'll go through and say, okay, where are each of these located? So it'll say, okay, where's file create A? Where's virtual protect? And it'll fill in those addresses. So now we know that where all the addresses are in memory, whatever application has this import table can say, okay, we've got all these different things. We can then access the function. So whenever you want to go create file A, it goes, okay, we need to go to and use this function at 7ff4008. So something's going on here. A little bit further on in the reverse engineering process, we're looking at a little bit of function, and there's something interesting going on here. Anybody recognize what this is happening here? It's those two highlighted functions I have. So we can see there's this, the first highlighted line. We can see that PCVAR1 is, you can see that there's a pointer to code for those of you C programmers. Basically, what's happening here is the result of this function that's being called, the function 0400402.086, is returning some kind of address of some function in memory. As a key part of what Ghidra is doing, it was able to tell, based on the fact that this PCVAR1 was used to call a function, it knows there's a function there, and then it can go through and say, okay, we need to analyze this like it's code. And then later on, we take the result, whatever address is returned from this weird function, we don't know what it does, and we call it with the arguments that are passed. So as a reverse engineer, from a Windows perspective, we say, okay, this is doing some kind of function lookup. And if we take a look at that first function a little bit deeper, we go look at it in the decompiler. We see some interesting text. Anybody? Bunch of Windows libraries. We might be getting a little bit closer to what we're looking for. This is a big hint here. It's trying to load these. Basically, if you go look at this function, it's loading these things into memory and doing some other stuff, which I'll get to in a second. So we know we're at least getting a little bit closer to the right track. And if you look at this is the cross references. This is where this thing is used, this function that we don't know what it does yet. We can see that it's used in a lot of different places, in this case 9. That tells us that this is kind of a framework thing. It's used in a bunch of different places. It's probably pretty integral to how it works. So I'm going to skip over a little bit here. now that we kind of got that framed, if we've gotten this far, we know where this function is probably doing its function lookups, getting the addresses of all these Windows API functions that it wants to use. I'm just going to go right to kind of how SpyEye does its function lookups and replaces this Windows functionality I talked about earlier. So basically what it boils down to is when it was being developed, what the SpyEye authors did is they took every single function name for Windows. Normally these appear in the binary. You can actually just basically look at it in a hex or text editor, and all those functions that we saw in the function import table will show up. So as an analyst, I can take a look at it and say, okay, yeah, this is using this one. I don't even have to decompile it. So that's, even starting out, that's pretty useful. But what SpyEye does is it hashes all these ahead of time. So instead of seeing all these strings, you see some, even if you look at the decompilation, you see a hexadecimal number. I actually forgot to mention it, but you can actually see this hash right here. There's this 32-bit number. This is the hash that it uses. This is some string that's been hashed. We're going to reverse that in a second. So what it does is instead of using Windows, SpyEye loads these libraries into memory itself. So it uses an undocumented function to do this, which actually bypasses, or at least at the time, would bypass a lot of antivirus checks. And basically, it goes through each exported function in the library. For example, if we're kernel32.dll, it would go through each of them. And usually these function lookups are done by name, so those names are included in the binary. And it goes through each one by one. And you've supplied this lookup function, the 32-bit hash that you want to see. It goes through and checks and hashes each exported function in this library and sees what it's matched what you've asked for. And if it does, it then, figures out what the address is of this function and returns it. Basically, in Windows terms, it's get proc address if you do payload development, stuff like that. But it's a lot stealthier. It doesn't show up in the binary itself. And going a little bit further down this path, you eventually come to this hashing function, which is going to be the key to this whole process going on later on. So what it is actually pretty simple. It's just takes those strings, does a little bit of bit shifting and exclusive ORing. It's up here in C if you're interested in seeing what it does. And from those strings, it generates a pseudo-random, not really, but value, 32-bit value that it uses to identify this function. Just an example, if you run this get hash function on load library A, it's going to generate 0xC8AC8026. So if this malware wants to call load library A, you're going to see, instead of load library A, you're going to see that value. So next step, how do we go with this? It's pretty easy to get a list of all the Windows API functions that exist. You can look it up online. There's tons of lists of them. And we know the encryption function. What do you do with passwords when you got this? You generate a rainbow table. Now, it's a little bit interesting because the number of different possible values is a lot smaller. Just based on the libraries that SpyEye uses, there were only, I think, 8,000. Well, it's still a lot, but there were 8,000 values. So this is something that normally, it would take you hours to generate on a GPU for passwords. But since it's a small enough data set here, it's actually pretty quick. We can generate it on the fly whenever we use the function that we're going to develop earlier. So the next step, of course, is to write some code to generate this rainbow table. When I was doing this analysis initially, I just basically wrote it in C because that is what I was comfortable with for doing bitwise arithmetic, which you can see is used in the function. And just to show you what this does, we tested it out just to see if this matches up, kind of makes sense. So we take this 32-bit value I have in this code we had from the earlier screenshot. And I have developed here, you can see in the command I have, ahead of time, I've got a list, where's my mouse, there it is, of kernel32 functions. I just picked one. So actually, I forgot to mention earlier, but this 0 in this lookup function that SpyEye has tells what library it's from. It's just, if it's 0, it's in this library. If it's 1, it's in another. And in this case, it's in kernel32.dll. And ahead of time, I had basically scraped off the internet, scraped a bunch of the list of of functions out of this library. You could actually, if you wanted to, use Ghidra to generate that list as well by going right through the actual binary headers. So we got this list. I then basically do some text processing to generate all these hashes for all those functions and basically create a mapping between those 32 values and the names. So what's that? And then I can just use grep to figure out, OK, this 976A, 979A, is it in that file? Sure enough, shows up. We can see that it says enumerate time format, so that's a Windows function. So we know that when in this particular case, what it's trying to do is trying to call enumerate time functions, or to enumerate time formats, sorry. So we've got a pretty solid process here. We can go and we can take any one of these functions, take that value and go look it up and figure out what it's actually trying to do. But it still addresses one problem. We saw that earlier that it was used in 9 different places. There actually, if you go and look at it, there's a couple different lookups that it does in slightly different ways. I haven't quite gone into the deep enough thing to make sure I had all of them. But that still represents a lot of tedious work of going, OK, here's the value. We're talking about a program that may have hundreds of thousands of instructions. It's still a pain in the butt to go do that. So we need to automate this. So, all right. Let's see where we're at. So we're going to develop an algorithm about this. I want to preface this by, when you're doing this kind of process, we really have to think about this as being kind of interactive programming. I don't know how many of you guys have had a chance to work with a system like R for data analysis, or Python like interactively in an interpreter. But one of the key things is when you're working on this, it's important to remember that what you're doing here doesn't have to be pretty. It doesn't even have to be efficient. It just has to work. And usually when you're doing this kind of stuff, it's on some kind of time frame. So it's important not to get too picky about your code quality. You just need to make it work. And it's even doubly so with malware, because whenever you develop for SpyEye, if I go to, I don't know, say working on configure, it's going to be totally different. I have to do something totally different. So you really got to treat this as, OK, I'm doing analysis, and I need to use this to support manual review of the code. This just basically takes the steps that we could do manually, and just makes the computer do them. All right, so talking about what we're going to do here. What we're going to do here, we're going to take advantage of Windows calling conventions. For those of you who don't know, when we saw the function with all the parameters, when a function is called, all of its arguments that you want to pass to this function are pushed onto the stack in reverse. So we had argument 1, 2, and 3. What would happen is that in the instructions, we would see 3 push instructions. We'd push the third argument, we'd push the second one, we'd push the first one onto the stack. And then there's a call, which actually moves the program counter to the routine. Now, we can take advantage of this when we're going through. Once we've done the analysis in Ghidra and it generates our disassembly and decompiler, we can just basically use those push instructions to find those values. So what we do, we generate our rainbow tables ahead of time. It only takes less than a second. So we can actually just do this whenever we run the script. And then once we got those lookup tables, the rainbow tables generated, we can just scan through the library, or the entire binary, starting at the beginning, and just look for every push instruction. Ghidra has a function to do this. I'll show it to you in a second when I pull up some source code of the script I've got. And we take a look at it and say, OK, is it 32-bit? Is it pushing a number? And if it's pushing a number, we then we'll say, OK, is it in our function lookup or in our lookup database? And if it is, we basically add a comment in the disassembly so we can see it later, and rename the function that the push instruction is in. Because most of the ways, and I think I'm beginning to question this assumption now, but I've looked at it a little bit closer, and I think it's a little bit not quite right. But at this point, what we're basically, the way SpyEye does its function lookups is it has each Windows function has its function that SpyEye has implemented. So basically, all that function does is it uses SpyEye's lookup code to find the address of the Windows API function and then calls it. So if we rename that external function that has lookup in it, we can then just say, OK, yeah, that's essentially like the Windows API function. We can move on from there. So I don't know if you guys can see this OK. Is this readable? Questionable? OK. I can actually try, and let me see if I can actually do a little bit of, is that better? Let me try this one more time. So we'll start here. Nope, that didn't work at all. Oh, kind of did. There. So what I've done here is this is not the entire script. I've just pulled out the parts. I didn't include up here. I didn't include the generation code for the rainbow tables because it's just reading from a file and writing back to it. But what we can see that there's this custom hash, which I've basically taken what I've gotten from the binary, and I've re-implemented it in Python. Just the same thing, input, and you get the output. I just want to add to this. I actually meant to talk about this in an earlier slide. One of the cool features that we were talking about, how Ghidra's modular, one of the cool features that you can do that would replace this is we can actually, because of this fact that we can go from binary to P code to pseudocode, we can actually emulate the CPU instruction by instruction for little sections of code, and we could just use the binary code that was already in there to do this for us. I didn't do it in here because I haven't had much of a chance to play with it yet, but that's kind of one of the next steps I'm going to be talking about later. Anyways, we got this function to do that. And let's go back here. All right, that did not work. Anyways, that's going to be a little bit more challenging to get work. What we do here, I'll pull up my mouse. First of all, this is our function. We currently get the program that's active in the editor. This is just basically, OK, what are we working on? And we just do some little bit of setup. And our first step is to get the address of the first instruction in memory. So this is the first thing that's successfully disassembled into an x86 instruction. And we basically loop through every instruction in the binary. Again, it doesn't take long. It takes maybe 5 seconds to run. And we, first of all, check if it's not a push instruction, we don't care about it. We can continue on. And we just skip the next one. And if it is push instruction, we want to get whatever is being pushed onto the stack. So we use, I talked about it earlier, we use get input objects. This basically says if it's a register, it'll tell you what the register is. If it's a constant value, you'll be able to see that constant value. And if it's a scalar number, as in if it's an integer or a float, we then check if it's 32 bits, and we get its unsigned value. And after that, it's pretty simple. If it's in the function database that we've already generated ahead of time, we know that it's a Windows API function that it's probably trying to handle here. And if it is and it matches and it shows up, we basically take the name of the function and annotate the source code. You can see there's a set comment command. This will show up in the decompiler and the disassembler. And initially, this was just all it did. It didn't do any renaming of functions or whatnot, but I added that. A couple days ago, I added the renaming. And then finally, we get the function that's the push instruction is inside, because it's generally one function lookup, and then you call it, and that's it. And we rename it. All right. So the process actually for those of you who are interested from user interface standpoint, we had that function, the script manager I showed you earlier with the 200 scripts. I've got loaded in there, I've got the spysearch.py, which is the source code you saw earlier in the previous slide. Double click it, and we see some console output. It tells you, OK, I found at this address, I found this Windows function. Things are going well. And the output's pretty cool. We can see a before and after. This is basically the code segment we saw where we've been kind of working on from the beginning. And we can see that there's a couple of different changes here. We can see that the function's been renamed, first of all. So we know that that function more or less is an analog for enumerate time formats. And there's actually one more step you do. You click a few buttons, and it also says, OK, I now know what kind of arguments it takes. We know what types they are. And you can also see that it's renamed some variables as well, because this basically matches the Windows docs now. And I think this is one example, but I think it's more illustrative is when you have functions that call this one, because those will look a lot different. We can see on the left, this is before it started. This is another function within SpyEye. You can see it's a lot different. We can see, for example, that a bunch of different variables in this function, which previously were listed as undefined, which is basically Ghidra's way of saying we don't know what this is. We just know it's 4 bytes or 32 bits. And since we can see that the Windows functions that SpyEye has tried to use have been labeled, and also the types that they take. So we know that since create mutex A, we'll go then that lowest arrow, since H object right there is the result of a call to create Mutex-A, we know that it's got a certain type based on the specifications that or that Microsoft has released for this library. And we can see above in the variable definitions that, or I think it's in there, maybe it isn't, that the types are made to match. You can see the win bool handle. Those are all just from what Ghidra knows about the Windows API and the fact that we've renamed all of our functions to match. It's pretty awesome. So next I want to go to takeaways, kind of what I want you to go away, end up coming away with. First of all, Ghidra's API is super powerful. It's extendable. You can write all this stuff to it. I mean, literally, what I've showed you here just scratches the surface. I talked about its ability to emulate code. It's going to make my life a lot easier once I figure it out. And future features are going to make it even better. There is talk that there is integration with debuggers in the future. It's been a little while since they said they were going to do that, but that's going to be pretty awesome. And it's still time-consuming and tedious, but this kind of automation, it's important to learn how to do it as part when you're learning how to be a reverse engineer, because without it, your effectiveness is pretty limited because of just the amount of time it's going to take. But I think even with all these tools, it's also important to say that having underlying platform knowledge is still critical to being a good reverse engineer. Along those lines, if there's any CISOs in the room, I just want to say that I cannot encourage you enough to get your team members using a tool like this. There's no cost to you as far as money. It's open source. And the skills that they will learn, even if it's taking something that's been detected by an antivirus tool or something maybe that isn't, that kind of is suspicious but didn't trip any detections, have them take a look at it and learn about it, because the knowledge you'll gain from that is pretty invaluable. And if you do use it, contribute back to it, because the more people use it and contribute and write code for it, the better it's going to be, which is really awesome. And with that, time for questions. Before I just want to go into questions, I want to thank a couple people. Colleen Coolidge from Segment for providing invaluable advice while this presentation was in the works, and especially my team at Coalfire Federal for also providing input on it as well. All right, with that, let's get into questions here for a second. I will pull them up. Has anybody got from the audience before I? Any? Are they in here? Yes. Okay, awesome. So he asked what the process is for working with a team on a single Ghidra project. This is actually an interesting question because one of the features that Ghidra has is it actually has the ability to do collaboration. At this point, it's kind of basic. So there's a server application that you can put on a server. It can be on your local laptop. It can be on a VPS somewhere. And then that server is set up. You add ability to add users to that. And then you, as part of the project creation process, you just basically say, OK, I want this to be a shared project. Say, OK, the server is hosted here. It goes and it does all this stuff. I will say that its features are good, but what I was kind of expecting and what I was hoping would be was not quite match that. It's a little bit, at this point, it's a little bit closer to being a version control system, really tailored to what Ghidra does. Its features are, check in, check out, get code. But it may change at that time. More people may develop those kind of solutions, which would be really cool to see. The ability to do like Google Docs style reverse analysis or reverse engineering would be awesome. I don't think it's there yet, but I'm hoping it gets there at some point. Any other ones? As far as versus IDA Pro, I haven't had a ton of time to compare the two directly. There's some things, and this may be a matter of perfect. By the way, he asked, how does it compare to IDA Pro? As far as, and this may be a matter of personal preference, there's some things that I like about Ghidra and how it lays things out and does certain analyses that I really prefer. I would say that in the what direct comparison I have done, it is pretty close to being the same. I haven't been able to get like a lot of we talked about data types in Windows and being able to detect those and annotate those. I haven't really been able to get IDA to do that quite as much. I think it may change a lot if you get Hexrays, the decompiler. I currently don't have a license for that right now. because Ghidra has worked pretty well for me so far, so there hasn't really been a need. But I think it's pretty close. I haven't looked at much as far as performance. The decompiler itself is in C++, so it's not terrible. It's pretty good. And so at some point I'll get to comparing those, but it's been, for someone who's getting into it, it's amazing. I think it's very, very near parity. Even the fact that you have as many support for many architectures, if you were to buy IDA with this many architectures, you're getting close to, you know, easily tens of thousands, maybe even hundreds of thousands of dollars to get all those. So almost the same, and I think a lot of that's, again, personal preference, but it's pretty darn close. Any other? Yeah.
So for the scripts, right, with Ghidra really, is there like a good library out there already, or is anything releasing one, or is anyone seasonally scripted and
Yes. So the question that was asked was, what libraries are there any libraries available as far as Ghidra scripting? It's an interesting question. One of the struggles I've had in going through Ghidra and learning it over the past, almost a year, is that the documentation is kind of there, but at some point you end up coming down to the point where you have to read the Java docs, which they are, and they're very good because Java docs are designed. That's one of the awesome features of Java. I will say that as far as libraries, haven't seen any external ones yet. I may just not have seen them. I'd say in a lot of cases, I would question the ability. Often when I'm dealing with these kind of things, I might take a script like that, and there's little teeny things that I want it to do, but it doesn't quite do. So generally my approach has been take the features in the Ghidra API, apply them specifically to the sample that I'm analyzing, and then when I go to another sample, you do that process again. There are places where you can generalize some of that, but at least at this point, I haven't really developed scripts that work on everything. And I think the approach is to, especially in these cases, develop for the software that you're analyzing. You can do it on the fly. It doesn't have to be pretty, like I said. But as far as libraries, I haven't seen anything out there. There is a big list here. A lot of scripts I haven't had a chance to play with, but I haven't seen anything other than that out there just yet. Get one more from the audience if there is, and then I'll go to the Slido. Let me see if I pull this up. Okay, let's see if I can find this here. Okay. I don't know if you have Slido up. If you be able to see, my phone might not be working, but you able to see questions? Yeah.
Have you ever ran into any situations with automation where you have functions inside the space
Yep.
that you're trying to automate, or like the hash function lookup?
So a gentleman over here asked whether we've encountered in situations where there's been collisions as far as the hashing algorithms, and I think this is actually an important question. I wish I'd covered a little. I probably should have covered a little bit more. But in this case, there is the potential for there to be collisions. I think since the amount of data that you're working with, like, hey, there's 8,000, 2 billion possible hash values and 8,000 instructions, the chances of that are going to be pretty low. It is something to keep in mind. In this case, in my case, it was a very conscious decision to avoid trying to be too specific, because in this particular case, if I get a false positive, it isn't the end of the world. At some point, it's going to come up, and I'll be like, this doesn't seem right. And I'll see that, and I'll say, okay, yeah, that's some weird edge case. It's more important for me in this case, since SpyEye does in a way, there's multiple ways of doing the same thing to some degree. It's more important that I get all of those, or close to all of them. So in this particular, I wrote that script with that in mind, which doesn't take into account collisions or pushing on some value of the stack that happens to be some hash of some Windows function. So it's something you should keep in mind when you're working with these, but in this particular case, I haven't seen anything yet. All right, any from the room, since there's none on the, yes? Okay, gentleman asked, as far as fingerprinting, is there a global database for like what we say with Flare? There are databases available on GitHub. I think what I've seen, and I may have forgetting something I've seen in the past, There are the FIDB function. The function ID is the function that is the functionality, what they call it in Ghidra. There are databases available for some libraries. I think there's one for Boost and a lot of like the general libc libraries in Linux. I haven't really seen one too much for Windows. More of the analysis that I've done so far has come from pulling out the imports. And I will say that in my experimentation with the function ID so far, I haven't had a ton of luck in getting it to detect with the databases I've had. And so I don't have a really good picture of how it works yet. But there are databases there. Is there one that's comprehensive? I haven't seen one yet. There are combinations of smaller ones that are specific to certain libraries. But I guess does that answer your question? Okay. Yeah, they're out there. I can think of one. I can if you come after. I can probably pull up the one that I have. But as far as Windows, I'd have to look some more to find it. Any others? All right. Well, thank you guys so much for coming out. I'll put my contact info will be up here for a second. Byron.roosa@coalfire.com. That'll work. Or I do have a Twitter account. It's kind of a ghost town right now. I don't really use it much, but I'll keep an eye on it over the next few weeks. At some point, I'm hoping I need to talk with people at Coalfire to just make sure everything's in line. But I'm going to try to take the Python script and put it up somewhere. That'll probably be through their online presence. All right, thank you.